Hello everyone, my name is Abebaw. I'm pleased to present my master research proposal titled Developing Context-Aware IoT Framework for Traffic Management in Addis Ababa City. This presentation has been prepared with the support of voice reading to enhance clarity, structure and visualization of the research content. Through this study to contribute to the improvement of urban mobility and intelligent traffic management in Ethiopia, capital city Addis Ababa, by integrating Internet of Things technology with context-aware principle. Let me start my presentation by using voice reading technology. Let's start together.
Under Federal TVT Institution, the Faculty of Electrical Electronics and ICT, Department of Information Communication Technology. Proposal title: Developing a Context-Aware IoT Framework for Traffic Management in Addis Ababa City. Submitted to Department of Information Communication Technology. Advisor, Associated Professor Mohammed Toon. Prepared by student, Abebaw Israel Dilbato. June 2025 Ethiopian Calendar. Addis Ababa, Ethiopia. Chapter 1, Introduction. 1.1 Background of the study. Rapid urbanization and population growth in developing cities, including Addis Ababa, Ethiopia, have led to severe traffic congestion, increased pollution, and frequent road accidents. The city's road infrastructure, originally designed for fewer vehicles, is now overwhelmed. Existing traffic management relies on fixed timing signals and manual police control, which are inadequate for dynamic, real-time challenges such as congestion, accidents, and emergencies. Advancements in Internet of Things, IoT, technology offer new opportunities for intelligent traffic management by enabling real-time data collection and adaptive control. However, effective deployment requires context-aware systems that can interpret situational factors such as time, location, weather, and traffic density to make informed decisions. In Ethiopia, current efforts are limited and lack integration of context-aware capabilities, mainly due to infrastructural and technological constraints. This study aims to develop a context-aware IoT framework tailored to the local conditions of selected zones like Meskel Square, Kotera Interchange, Mejanaga up to Lambaret Square, Cities Kilo Yekatai 12 Square, Torhalik Hospital and other area, integrating sensor technology, real-time data analysis, and adaptive decision-making to improve traffic flow and safety. 1.2 Statement of the problem. Addis Ababa faces escalating traffic congestion due to rapid population growth, unplanned urban expansion, and increasing vehicle numbers. The current traffic management system, based on fixed timing signals and manual intervention, cannot adapt to real-time conditions, resulting in inefficiency, increased pollution, and safety risks. Existing technological upgrades are fragmented and lack real-time, context-sensitive integration. The absence of a comprehensive, locally adapted intelligent traffic management framework exacerbates these challenges, hindering the city's transition to a modern, efficient urban environment. 1.3 Research questions. This study is guided by the following questions. 1. What are the major traffic management challenges in Addis Ababa, and how do they affect urban mobility and safety? 2. To what extent is IoT technology currently utilized in the city's traffic management? 3. What contextual factors are most relevant for effective real-time traffic management? 4. How can a context-aware IoT framework be designed to adapt to changing traffic conditions? 5. What are the technical requirements and architectural components for such a framework? 6. How does the proposed framework compare with existing approaches in terms of performance and scalability? 7. What are the challenges and limitations of implementing context-aware IoT traffic management in Ethiopian cities? 1.4 Objectives 1.4.1 General Objective to develop a context-aware IoT framework that enhances real-time traffic management and decision-making in Addis Ababa. 1.4.2 Specific Objectives Assess the current use and readiness of IoT technologies in the city's traffic infrastructure. Identify key contextual factors affecting real-time traffic management. Design an architectural framework integrating context-aware computing and IoT for adaptive control. Simulate or prototype the framework and evaluate its performance. Compare the proposed framework with existing practices. Explore practical challenges and policy considerations for city-wide implementation. 1.5 Significance of the research. This research addresses urgent urban traffic challenges by introducing a locally adapted, intelligent IoT-based traffic management framework. The system aims to reduce congestion, save travel time, minimize emissions, and improve safety by enabling adaptive, context-aware control. The study provides practical insights for policymakers, urban planners, and researchers, and contributes to the advancement of smart city initiatives in Ethiopia. 1.6 Scope and Limitations Research. 1.6.1 Scope. The study focuses on the design and implementation of a context-aware IoT traffic management framework for major congestion zones. It emphasizes real-time data collection, context analysis, and adaptive signal control, evaluated in simulated environments. The research does not include full-scale hardware deployment or address all possible contextual variables. 1.6.2 Limitations. Key limitations include the lack of real-time, high-frequency traffic data, absence of real-world deployment, infrastructural constraints, example weak connectivity, limited contextual variables, and the framework's specificity to Addis Ababa's context. Resource and time constraints further limit large-scale testing and integration with government platforms. 1.7 Organization of the thesis. Chapter 1, Introduction, Background, Problem Statement, Research Questions, Objectives, Significance, Scope, and Limitations. Chapter 2, Literature Review, Urban Traffic Management, IoT, Context-Aware Systems, and Research Gaps. Chapter 3, Methodology, Research Design, Data Collection, Study Area, Analysis, and Ethics. Chapter 4, System Design and Framework Development, Requirements, Architecture, and Integration. Chapter 5, Evaluation and Experimental Results, Implementation, Testing, Metrics, and Comparative Analysis. Chapter 6, Summary, Conclusion, and Recommendations, Findings, Conclusions, and Future Direct. Chapter 2, Literature Review. 2.1 Introduction. This chapter reviews key literature relevant to the development of a context-aware Internet of Things, IoT, framework for urban traffic management. The review is organized into theoretical, empirical, and conceptual categories, with a focus on urbanization, intelligent transportation systems, ITS, context-aware computing, IoT applications, wireless sensor networks, WSNs, and the integration of context awareness into traffic systems. Special attention is given to the unique challenges and technological constraints in the local context. The chapter concludes by identifying research gaps that justify the present study. 2.2 Theoretical Literature Review. 2.2.1 Urbanization and Mobility in African Cities. Rapid urbanization in Africa is projected to result in over 60% urban population by 2050, on Habitat, 2022. This growth has outpaced transportation infrastructure, leading to chronic congestion and inefficiency. Poor urban planning, underdeveloped public transport, and the proliferation of private vehicles are major contributors to traffic challenges in sub-Saharan African cities. World Bank, 2021. 2.2.2 Intelligent Transportation Systems, ITS. ITS represents a modern approach to urban mobility, speed and environmental conditions, supporting adaptive traffic control. WSNs are cost-effective and flexible but require energy-efficient protocols to address power and reliability challenges. Lynch and Lowe, 2006. 2.3.3 Context Awareness in Urban Mobility. Context-aware systems in smart cities leverage real-time data from various sources to optimize mobility and safety. Rocha et al., 2022. These systems use both primary, location, activity, and secondary, speed, pedestrian movement, context attributes to adapt dynamically to changing urban conditions. 2.4 Conceptual Literature Review. 2.4.1 Components of Context-Aware Traffic Systems. Key components include context acquisition, modeling, reasoning, repositories, distribution, and visualization. Schmidt, 2019. These elements enable traffic systems to collect, interpret, and act on contextual information, supporting intelligent and adaptive management. 2.4.2 Frameworks for Context-Aware IoT. Frameworks such as the 5-layer IoT model, Sethi and Sorangi, 2017, Rahman, 2022, and the Context Toolkit, Day and Abode, 2001, provide modular, scalable architectures for integrating heterogeneous data sources and supporting real-time, adaptive traffic management. 2.5 Existing traffic management in the city. 2.5.1 Infrastructure and organizational challenges. The city's Traffic Management Bureau faces limitations due to outdated infrastructure, static signals, and weak interagency coordination. Most intersections are managed manually or with fixed timing. 2.5.2 Data collection and use. While some intersections have cameras, data is not fully utilized for intelligent control. There is no integrated system for real-time, context-aware traffic management. 2.5.3 Public transport and road user behavior. Public transport is not optimized or integrated into traffic control, and informal driving practices exacerbate congestion. These factors highlight the need for intelligent, data-driven traffic management. 2.6 Gaps in current research. Despite global advances, research tailored to the Ethiopian context is limited. Existing studies often neglect local traffic behaviors, infrastructural constraints, and stakeholder engagement. There is a lack of localized models and minimal integration of real-time contextual data. Simulation-based evaluations and participatory development are also lacking, underscoring the need for a context-aware IoT framework suited to local realities. 2.7 Summary. This chapter reviewed theoretical, empirical, and conceptual literature on context-aware IoT frameworks for traffic management, with a focus on the challenges and realities of the local context. While global studies demonstrate the potential of IoT and context-aware systems, significant gaps remain in their application to the unique conditions of the city. Addressing these gaps is essential for developing effective, sustainable traffic management solutions. Chapter 3 Methodology 3.1 Introduction. This chapter presents the methodology adopted for the development of a context-aware IoT framework for traffic management in Addis Ababa city. The methodology explains the systematic process used to design, implement, and evaluate the framework. It integrates both technical system design principles and social research techniques to ensure that the solution is not only scientifically valid but also locally relevant. The methodological design emphasizes a mixed methods approach, combining qualitative, interviews, surveys, and observational studies, and quantitative, traffic counts, statistical analysis, and simulation-based evaluation, strategies. This ensures that both human factors, behavior of commuters, attitudes of stakeholders, and institutional practices, and technological factors, sensor performance, algorithms, and network reliability, are adequately considered. The chapter is organized into key sections, including research design and approach, phases of the research, data collection methods, sampling techniques, data analysis, and evaluation. Each section is carefully aligned with the research objectives and the need to build a scalable, reliable, and adaptive IoT traffic management framework. 3.2. Research design and approach. 3.2.1. Overall design. The study follows the design science research, DSR, methodology, which is well suited for projects that involve designing, building, and evaluating technological artifacts. Unlike purely descriptive or theoretical research, DSR is practical and problem-oriented, making it ideal for addressing complex urban traffic issues in Addis Ababa. The DSR process is iterative, allowing refinements at different stages. Each iteration incorporates stakeholder feedback, simulation results, and contextual adjustments to ensure the framework aligns with real-world conditions. The approach is applied, in that it directly addresses a societal challenge, traffic congestion; descriptive, in that it captures existing patterns of traffic flow and management inefficiencies; and exploratory, in that it develops new insights into the role of IoT and context awareness in traffic systems. 3.2.2. Research phases. 1. Exploratory phase. The exploratory phase involved conducting a comprehensive literature review to understand the state of IoT in smart cities and traffic systems globally. In addition, consultations were held with key stakeholders, including traffic police, city planners, and transport experts, to identify the most pressing traffic challenges in Addis Ababa. This phase also focused on gathering context-specific constraints such as limited road infrastructure, unreliable internet connectivity, and budgetary limitations that could influence system deployment. 2. Development phase. The development phase focused on designing the IoT framework architecture, which incorporated sensor networks, communication modules, a context awareness engine, and adaptive decision-making algorithms. During this stage, implementation models were developed to represent critical intersections in Addis Ababa, including Meskel Square, Gotera Interchange, Mejanagna up to Lambaret Square, Sidist Kilo Yekatai 12 Square, and the Torhalik Hospital intersection, among others. Context-aware modules were also designed to interpret real-time variables such as traffic density, weather conditions, emergencies, and time-of-day variations, ensuring that the framework could adapt to diverse and dynamic urban conditions. 3. Evaluation phase. The evaluation phase involved rigorous testing and simulation experiments to measure the efficiency and responsiveness of the framework under different traffic scenarios. Feedback was gathered from urban planners and traffic authorities to assess the usability and feasibility of the proposed solution. Finally, the performance of the context-aware IoT system was compared with baseline traffic control methods currently applied in Addis Ababa, providing insights into improvements in traffic flow, adaptability, and overall system effectiveness. 3.2.3. System design focus. The IoT framework is designed to integrate 4 core components that work together to ensure intelligent and adaptive traffic management. First, sensor networks consisting of IoT-enabled traffic sensors, vehicle-mounted GPS units, and roadside devices are employed to capture real-time traffic data. Second, a context awareness engine functions as middleware, processing contextual inputs such as vehicle density, time of day, weather conditions, and emergency events to support adaptive decision-making. Third, data flow and communication are structured through edge devices, gateways, and central servers using lightweight protocols such as MQTT and CoAP to ensure reliable and scalable data exchange. Finally, adaptive traffic signal control algorithms dynamically adjust signal timings to optimize vehicle flow and reduce congestion based on the processed contextual information. To minimize risks and costs before actual deployment, simulation tools are used to evaluate the performance of the framework under varying traffic conditions. 3.2.4 Justification of the approach. This approach was selected because it balances technical innovation through IoT devices, real-time analytics, and adaptive algorithms with practical applicability in a developing city context like Addis Ababa. The framework emphasizes iterative testing using simulation models, ensuring system reliability and effectiveness prior to large-scale deployment. Moreover, it integrates both technical parameters such as latency, throughput, and energy efficiency of sensors, and contextual variables including driver behavior, road conditions, and socio-economic constraints. This dual consideration ensures that the system remains both technologically robust and contextually relevant, thereby increasing the likelihood of successful adoption and long-term sustainability. 3.3 Data collection methods. The study employed a combination of primary and secondary data sources to ensure a comprehensive and contextually relevant data set. Primary data were gathered through direct observations at 6 high-traffic intersections in Addis Ababa, where vehicle counts, peak hour congestion levels, and pedestrian movements were systematically recorded. In addition, structured surveys were conducted with 200 commuters and drivers to capture experiences with congestion, delays, and perceptions of technology-based solutions. Complementing these were semi-structured interviews with 15 key informants, including traffic officials, urban planners, and ICT specialists, which provided deeper insights into institutional perspectives and operational challenges. Secondary data were also incorporated, including traffic and accident records from the Addis Ababa Traffic Police Commission and municipal transport authorities, geospatial data, GIS and satellite imagery, to model intersections and evaluate traffic density distributions, and a comprehensive literature review of global case studies in IoT-based traffic management and smart city frameworks, which served as benchmarks for the proposed system. 3.4 Sampling techniques. Multiple sampling strategies were applied to ensure the representativeness and reliability of the collected data. Purposive sampling was employed to select traffic officials, ICT experts, and urban planners for interviews due to their specialized knowledge and direct involvement in traffic management systems. Stratified random sampling was applied to commuters or people who travel regularly between their home and workplace, school, or other daily destinations, and drivers, categorizing them by occupation, frequency of travel, and routes before random selection, thereby ensuring diverse representation of Addis Ababa's road users. Additionally, convenience sampling was used to select high-traffic observational sites such as Mescal Flower and Gotera interchange based on accessibility and their significance as congestion hotspots. This multi-method sampling approach guaranteed both depth and breadth in capturing traffic-related realities. 3.5 Data analysis. 3.5.1 System requirements analysis. The analysis of system requirements distinguished between functional and non-functional needs. Functional requirements included real-time data acquisition, adaptive traffic signal control, and priority handling for emergency vehicles, while non-functional requirements emphasized scalability, reliability, security, interoperability with existing infrastructure, and maintainability. These requirements guided both the design and evaluation phases of the IoT framework. 3.5.2 Quantitative analysis. Quantitative analysis was carried out using both descriptive and inferential techniques. Descriptive statistics such as means, frequencies, and percentages summarized survey responses on congestion patterns and delays. Inferential tests, including ANOVA and regression models, were applied to investigate the relationships between traffic congestion and contextual factors such as weather conditions, time of day, and road types. This provided statistical evidence on the factors influencing Addis Ababa's traffic dynamics. 3.5.3 Qualitative Analysis. Qualitative data from interviews were analyzed thematically, allowing key issues to emerge from participant responses. Insights were extracted on institutional challenges, enforcement gaps, and user perspectives on adopting technology-driven traffic solutions. Major themes included infrastructure limitations, policy and regulatory gaps, and cultural attitudes toward road use. These qualitative findings added depth to the quantitative evidence, ensuring that the proposed framework addressed not only technological requirements but also socio-institutional realities. 3.5.4 Simulation and Comparative Analysis. Simulation played a central role in evaluating the performance of the proposed framework. Tools such as NS3 and Sumo were used to model traffic under various scenarios, replicating real-world intersections in Addis Ababa. The performance of the context-aware IoT framework was then compared with existing baseline traffic management systems. Metrics such as latency, throughput, traffic flow efficiency, and accident reduction potential were analyzed to determine the extent to which the new framework improved upon current practices. 3.5.5 Triangulation. To ensure validity and reliability, the study applied triangulation by integrating findings from multiple data sources. Observational data, survey responses, interview insights, simulation outputs, and institutional reports were cross-verified. This approach minimized bias, enhanced data credibility, and reinforced the robustness of the conclusions. 3.6 Ethical Considerations. Strict ethical guidelines were observed throughout the study. Informed consent was obtained from all survey and interview participants, ensuring voluntary participation. Confidentiality was maintained by removing personal identifiers and anonymizing responses in the analysis. The research adhered to principles of academic integrity, with all external sources properly acknowledged. Furthermore, data security protocols were implemented to safeguard sensitive traffic information and personal data collected during the study. This chapter has outlined the methodology employed in developing a context-aware IoT framework for traffic management in Addis Ababa. By applying the design science research methodology, the study combined iterative design, mixed method data collection, and multi-level analysis to balance technical innovation with contextual realities. Observations, surveys, interviews, simulation models, and triangulation ensured both empirical accuracy and practical relevance, while ethical considerations reinforced the credibility of the research process. Together, these methodological choices establish a solid foundation for the subsequent system design and implementation presented in the following chapter. This chapter outlines the strategic work plan designed to implement the research project. It includes detailed tasks, a financial budget, and a timeline for the execution of research activities. The purpose is to ensure that the project is feasible, well organized, and conducted within the available time and resource constraints. This plan is structured into three main sections: the budget, the timeline, and the estimated work breakdown structure, WBS. 5.1 Budget. The following budget breakdown provides previously used detailed estimate of the costs involved in conducting the research on a context-aware IoT framework for traffic management in Ethiopia. These costs cover all aspects of the research, including personnel data collection, materials, and miscellaneous expenses. Detailed budget in Ethiopian Standard or ETB. 1. Personnel costs. Item 1.1, Research Assistance, Data Collection and Analysis. Cost in USD, $2,000. Cost in ETB, 289,280 ETB. Description: 2 assistants for field data collection, surveys, interviews, and data analysis. Item 1.2, Survey facilitators or interviewers. Cost in USD, $1,200. Cost in ETB, 173,568 ETB. Description: facilitate surveys, conduct interviews, and organize focus groups. 2. Data collection costs. Item 2.1, Survey Platform Subscription. Cost in USD, $100. Cost in ETB, 14,464 ETB. Description: subscription to an online survey platform. Item 2.2, Audio recorders and transcription services. Cost in USD, $300. Cost in ETB, 43,392 ETB. Description: for recording and transcription. Item 2.3, Incentives for participants. Cost in USD, $500. Cost in ETB, 72,320 ETB. Description: gift cards or financial incentives. Item 2.4, Transportation and fieldwork expenses. Cost in USD, $400. Cost in ETB, 57,856 ETB. Description: travel within Addis Ababa. 3. Materials and equipment. Item 3.1, Computers and software, SPSS, NVivo, etc. Cost in USD, $800. Cost in ETB, 115,712 ETB. Description: software licenses and computer resources. Item 3.2, Printing surveys, consent forms, and reports. Cost in USD, $200. Cost in ETB, 28,928 ETB. Description: printing physical documents. 4. Travel and accommodation. Item 4.1, Local travel for stakeholder meetings. Cost in USD, $600. Cost in ETB, 86,784 ETB. Description: local travel for meetings and field work. Item 4.2, Accommodation for field work. Cost in USD, $400. Cost in ETB, 57,856 ETB. Description: overnight stays during field work. 5. Miscellaneous. Item 5.1, Contingency Fund. Cost in USD, $300. Cost in ETB, 43,392 ETB. Description: reserved for unexpected expenses. 6. Total. Cost in USD, $6,400. Cost in ETB, 926,712 ETB. Description: total estimated project budget. 5.2 Timeline. A timeline outlines the key activities, milestones, and deadlines over the course of the research project. It helps in managing time, tracking progress, and ensuring timely completion of tasks. Project timeline and phases. Phase 1, Literature Review. Task: review existing literature on IoT, context-aware systems, and Ethiopian traffic challenges. Start date, month 1. End date, month 1. Duration, 4 weeks. Details: collect and analyze relevant studies and documents to build a theoretical foundation for the research. Phase 2, Research Design. Task: finalize methodology and design surveys, interviews, and focus group protocols. Start date, month 1. End date, month 1. Duration, 2 weeks. Details: develop research instruments and strategy to guide data collection and analysis. Phase 3, Data Collection. Task: conduct surveys, interviews, and focus group discussions. Start date, month 2. End date, month 3. Duration, 6 weeks. Details: collect primary data from stakeholders including drivers, commuters, and traffic officials. Phase 4, Data Analysis. Task, analyze quantitative and qualitative data. Start date, month 3. End date, month 4. Duration, 4 weeks. Details, process quantitative data using SPSS/Excel and qualitative data using NVivo, then interpret results. Phase 5, Simulation and Modeling. Task, develop models and simulate IoT-based traffic solutions. Start date, month 4. End date, month 5. Duration, 4 weeks. Details, evaluate the impact of proposed traffic management solutions through modeling and simulation. Phase 6, Report Writing. Task, draft findings, create visuals, and compile the final report. Start date, month 5. End date, month 6. Duration, 4 weeks. Details, prepare comprehensive documentation of the research, including charts, diagrams, and written analysis. Phase 7, Final Review. Task, revise and finalize report based on feedback. Start date, month 6. End date, month 6. 5.3 Work Breakdown Structure, WBS. A work breakdown structure, WBS, decomposes the project into manageable sections. This helps in resource allocation, timeline management, and task monitoring. 1.0 Literature Review. Description, review prior studies and theoretical frameworks relevant to the research. Duration, 3 weeks. Predecessor. 1.1 IoT in Traffic Management. Description, review existing IoT applications in traffic management systems. Duration, 1 week. Predecessor, 1.0. 1.2 Context-Aware Systems. Description, study concepts and applications of context-aware computing. Duration, 1 week. Predecessor, 1.0. 1.3 Traffic in Addis Ababa. Description, review local traffic challenges, congestion patterns, and existing management strategies in Addis Ababa. Duration, 1 week. Predecessor, 1.0. 2.0 Research Design and Instruments. Description, define the research methodology and design instruments such as surveys, interviews, and data collection tools. Duration, 2 weeks. Predecessor, 1.0. 3.0 Data Collection. Description, collect primary data through IoT sensors, interviews, surveys, and other methods. Duration, 4 weeks. Predecessor, 2.0. 3.1 Sensor Deployment. Description, deploy IoT sensors at selected traffic locations to collect real-time data. Duration, 2 weeks. Predecessor, 2.0. 3.2 Interviews and Surveys. Description, conduct stakeholder interviews and administer surveys to collect qualitative and quantitative data. Duration, 2 weeks. Predecessor, 2.0. Conclusion: this study demonstrates the potential of a context-aware IoT framework to significantly improve traffic management in rapidly urbanizing cities like Addis Ababa. By leveraging real-time data from various sensors and employing adaptive response mechanisms, the proposed system can optimize traffic flow, reduce congestion, and enhance road safety despite existing infrastructure limitations. The integration of IoT technologies tailored to local traffic conditions provides a promising, scalable, and sustainable approach to addressing urban mobility challenges in Ethiopia. Future work should focus on piloting the framework in real-world settings and further refining it based on stakeholder feedback and evolving urban dynamics. References and citation. Day, A.K., and Abebaw, GD, 2001. A conceptual framework and a toolkit for supporting the rapid prototyping of context-aware applications. Human, Computer Interaction, 16, 2-4, 97-166. ISO 2023, Intelligent Transportation Systems, Transforming Modern Mobility. International Organization for Standardization. Kenya Urban Roads Authority. 2021, Nairobi Smart Traffic Lights Pilot Project Report. Lynch, J.P., and Lowe, K.J., 2006. A summary review of wireless sensors and sensor networks for structural health monitoring. Shock and Vibration Digest, 38, 91-130. Prasad, R., 2018. Context-Aware Computing and Smart Environments. Wiley. Rahman, M.A., 2022. Internet of Things, IoT, Architecture and Protocols. Springer. Rocha, N.P., Diaz, A., Santinha, G., Rodriguez, M., Rodriguez, C., Quiros, A., Bastardo, R., and Paveo, J., 2022. Context-Aware Applications in Smart Cities, a Review. Sensors, 22, 3, 1056. Schmidt, A., 2019. Context-Aware Computing, Context Awareness, Context-Aware User Interfaces, and Context-Aware Systems. In Human-Computer Interaction Series. Springer. Sethi, P., and Sarungi, S.R., 2017. Internet of Things, Architectures, Protocols, and Applications. Journal of Electrical and Computer Engineering, 2017, 932-4035. On Habitat. 2022, World Cities Report 2022, Envisaging the Future of Cities. USDOT. 2020, Intelligent Transportation Systems Strategic Plan 2020-2025. U.S. Department of Transportation. World Bank. 2021, Urban Transport in Sub-Saharan Africa, Improving Accessibility and Safety. Zanella, A., Bui, N., Castellani, A., Vangelista, L., and Zorzi, M., 2014. Internet of Things for Smart Cities. IEEE Internet of Things Journal, 1, 22-32. Thank you.